I want you to imagine a fire alarm, right? But instead of detecting smoke and, ringing a bell to warn you, it detects smoke and just immediately combusts.
Oh, wow. Yeah, that's not ideal.
Right. It doesn't warn you. It doesn't, fail safely. The exact mechanism that's supposed to alert you to this catastrophic failure just becomes the source of a secondary terminal explosion.
Which completely defeats the purpose of the alarm.
Exactly. And so, that exact paradox is playing out inside, millions of lines of code right now. And the crazy part is it's entirely avoidable. So welcome back to the deep dive.
Glad to be here for this one.
Yet today we are really getting into the architecture of failure. And we're doing it through this incredible lens, some developer notes we received from a software engineer named Ang.
Yeah, specifically an entry titled Notes on Haskell Programming Part 166.
Right, dated June 19, 2026. And the mission here today isn't just to, debug some random snippet of code. We are really looking at a profound engineering hazard.
A huge hazard, yeah. The use of what we call partial versus total functions.
Exactly. And, what happens when the very safety nets we build are just fundamentally flawed?
Okay, let's unpack this. Ang ran into this specific situation that, frankly, every systems architect is going to face eventually, right?
Oh, absolutely. You build an application, and you know things are going to go wrong eventually, so you build an error handler to catch those faults.
Right, a safety net.
Exactly. But Ang documents this terrifying scenario where the error handler itself encounters an anomaly, while it's trying to process the original error.
So the fire alarm catches fire.
The fire alarm catches fire.
Yep.
And instead of degrading gracefully or, just giving you a basic warning, the handler triggers a hard crash. The entire program just evaporates.
It's wild. Let's get under the hood of how that evaporation actually happens, because Ang points to a very specific culprit in their Haskell code. It's a function called decode UF8.
Right.
And on the surface, if you're just reading the code, decoding UTF-8 sounds like standard janitorial work.
Just cleaning things up. Yeah, exactly. A fault occurs, the system captures some raw byte data related to that fault, and it just needs to translate those raw bytes into human-readable text.
So the developer can actually log it or show it to the user.
Right. But things go off the rails here.
What's fascinating here is the paradox of the whole situation. The error handler is trying to convert data to tell the user what went wrong, but the tool it's using, that decode UTF-8 function, is inherently unsafe for this specific context.
Why is it unsafe, though? UTF-8 is everywhere.
It is everywhere, but we have to look at the mechanics of what UTF-8 actually is. It's a variable with character encoding standard. So a single character might just be 1 byte, or it could take up to 4 bytes.
Okay, so it varies.
Right, and because it varies, it relies on this very strict structural sequence to know where a character begins and ends. But think about when a program enters a false state.
Like if a network connection just drops unexpectedly.
Exactly. Or, memory gets corrupted. The raw data the system spits out in that moment is often mangled. It's truncated. You might literally just get half of a 4-byte sequence.
Which means the byte stream is just fundamentally invalid. It doesn't map to the standard at all.
Precisely. And here is the mechanical track Ang ran into. The decode UTF-8 function is asked to read this mangled byte stream, but it has no internal fallback for invalid sequences. It doesn't know how to render half a character.
It just panics.
It panics. And because of how it was written, it doesn't return an error type that the program can examine. It just throws a runtime exception immediately.
Wait, if it just immediately throws a runtime exception on bad input, why would anyone use it in an error handler?
Well, that's the multi-million-dollar question, isn't it?
It's like building a vending machine where if you put in a fake coin, instead of just returning the rejected coin to you, the entire machine just explodes.
That is a perfect analogy. And honestly, it's exactly the conclusion Ang reached. Using a partial function, which is what this is, in an error handler is fundamentally unsafe.
Let's define that term real quick, because Ang uses it a lot. Partial function. It sounds like, an unfinished piece of code.
Right, like somebody forgot to type the rest of it. But mathematically, in set theory, a true function maps every single element of an input set to an output. A partial function only maps a subset of the input domain.
Meaning there are inputs it just doesn't have answers for.
Exactly. If you feed it an input outside that expected subset, like our truncated UTF-8 byte sequence, the math has no answer. It's strictly undefined.
And in software, undefined behavior is basically just a fancy phrase for a catastrophic crash.
Oh, 100%. And look, developers use partial functions all the time, usually for performance. If you can guarantee that the data is pristine, a partial function is incredibly fast.
Because you aren't wasting CPU cycles checking for errors that, theoretically can't happen.
Right. But that logic completely falls apart the second you place that partial function inside an error handler.
Because the error handler is the one place where you absolutely know things have already gone wrong. The invariants are already broken.
Exactly. You can't guarantee the integrity of the data because the system is literally in the middle of reporting a failure. Ang realized that to use decode UTF-8 safely, you'd have to wrap the translation process itself in its own complex error handling logic.
So you're just writing error handlers for your error handler.
Yes. You end up trying to catch the mistakes made by the tool you brought in to catch the original mistakes. It's a nightmare.
It's like an endless nesting doll to fragility. If your error translation fails, how do you report that failure? You need another handler, which logically leads Ang to search for a safer alternative, the antidote to all this.
Right. Which brings us to the total function.
Yes, the total function. So if a partial function only works some of the time, the total function is the safety net, right?
Precisely. Ang uses the show function as the primary example here. And show is brilliant because it works in stark contrast to decode UTF-8.
How so? Like, what does show actually do differently?
So a total function is mathematically defined for every possible input within its domain. There is no undefined state. When show is invoked, it doesn't try to interpret the semantic meaning of some raw byte sequence against an external standard like UTF-8.
Doesn't care about the standard.
It doesn't care at all. It just looks at the structure of the data type it's given, and it maps that structure to a string representation. Even if the data itself represents a corrupted, broken state, the structure of the data type remains intact within the Haskell runtime.
So what does this all mean for you listening? It means reliability. It's the difference between hiring a translator who just quits and throws a tantrum if they hear a word they don't know.
The partial function.
Right. Versus a reliable translator who will always give you some kind of readable string, even if it's just literally describing the garbled noise they heard.
Exactly. It's the guarantee of delivery. That guarantee is the most valuable currency you can possibly have in an error handler.
You want absolute certainty that your distress signal is actually going to be sent.
Yes. By using a total function, you absorb the chaos of the broken system state, and you output predictable, reliable information. The program still shuts down, sure, but it successfully logs the fault and exits gracefully instead of just evaporating.
But here's where it gets really interesting. What if the data type doesn't implement that show type class? Ang mentions this condition, right? That show only works if the data type has that implementation.
Right, there is that dependency.
So what if I'm a developer and I create this massive, complex, custom data type like a connection pool manager, and I just forget to implement show for it? Does it crash then? Does my total function suddenly become a partial function and blow up the system?
No. And this is the magic of Ang's whole analysis. It doesn't crash at runtime. Instead, you get a compile time error.
Wait, so the program never even runs?
It never even runs. If we connect this to the bigger picture, this is why a compile time error is vastly superior to a runtime exception.
Because it catches it in the lab.
Exactly. Haskell uses its type system like an automated mathematical proof. When the compiler reads the code and sees you trying to use show on your connection pool manager, it actively searches for a show instance for that specific type.
It needs proof that a mapping exists before it even builds the software.
Right. And if it can't find that proof, it just halts the build immediately. It says, I cannot mathematically prove that this operation will succeed, so I refuse to compile this into an executable.
That is just so vastly different from how dynamically typed languages work.
Right.
Like, in Python or Java, it'll happily compile and it's just sitting there like a landmine waiting for the user to step on it.
Exactly. A runtime exception happens in the user's hands. A compile time error happens on the developer's desk. It guarantees type safety and entirely prevents this specific scenario where the software crashes while trying to report an error.
So Ang's final takeaway is essentially keep partial functions completely out of your error handlers.
Keep them far, far away.
Yeah, to avoid introducing these fatal blind spots into your code's safety mechanisms. I mean, synthesizing all this, we've gone from the really ironic, explosive crash of decode UF8,
The fire alarm catching fire.
right, to understanding just how volatile partial functions can be in the wrong context. And finally, finding that bulletproof reliability of total functions like show, backed up by compile time type safety.
It really reframes how you look at system design. Understanding the tools we use to catch mistakes is literally just as important as trying to avoid the mistakes in the first place.
It really is.
Because if partial functions can hide silently inside the very systems designed to report errors, causing the system to instantly self-destruct instead of speaking up, it really makes you wonder.
Wonder what?
Well, how many silent crashes in the software you rely on every day are just a result of an error handler encountering an error it wasn't equipped to translate?
Yep.
Right, like how many system failures aren't actually core logic failures, but just the distress beacon failing to fire?
That is a deeply unsettling thought to leave on, but a vital one. Thank you so much for joining us on this deep dive into Ang's notes, and we invite you to join us next time as we keep exploring the hidden architectures running our world.